Hi, this is the OpenFoam tutorial for how to make a dynamic mesh. In order to follow this tutorial, you're going to need to know the basics of OpenFoam and the general parameters we're going to use, as well as how to use the basics of block mesh, SnappyHexMesh, and we're using a way to create the block mesh dict files as M4 macros. And that's pretty useful. That's going to be partially explained, but some background on that is going to be necessary. What we're actually covering in the video is the cyclic AMI, the arbitrary mesh interface, and the cell zone, and how to specify what moves in a dynamic mesh. And then we're going to run it, go through some examples, change it as we go, and then run it. The initial mesh will look like a cylinder and cross flow. This is only done to demonstrate a static mesh before we move on to a dynamic mesh, so we can show you what changes need to be made in order to actually make the dynamic mesh. That make mesh command was a bash script that we need to use in order to actually create the block mesh dict file here with this M4 macro and then run it. The mesh that we just made looks like this. Right now, we're not actually running the part in the center here. This boundary here is a wall right now. It's the same as the top and bottom walls. So the fluid will really just flow around this cylinder here. It'll come in from this inlet, then exit here, and it'll go around that cylinder. We'll show you that now. What we just did here is ran the like this, like it's a regular wall. You'll see now that it does follow around the proper pattern. This gap right here, no fluid flows across it. This is the first problem. As this inner region moves, it's going to have to talk to the outer region, and we can't do that because the points will just slip right past each other, and we need some way to get these two faces to be able to talk and then recalculate which faces are talking to the other faces at each time step. This is critical, and this is called the cyclic AMI. We're going to do that now. We clean what we just ran with all clean. That's run in make mesh anyway. That was unnecessary. I just wanted to make that clear. We're going to make the mesh again. This is the same mesh as before. I'm just using it as an example. Again. AMI 1 right now is a wall. We can see it in the block mesh dict file. Fluid does not cross this gap. This is what we're changing right now. In order to make these two boundaries right here, AMI 1 and AMI 2, talk to each other, we have to change that in block mesh. It's done like this. We change this part to cyclic AMI. We next say the neighbor patch is AMI 2, so we know which cyclic AMI patch is going to talk to. We apply this same thing. We change this AMI 2 to a cyclic AMI as well, and change this neighbor patch to 1, because this AMI2 talks to AMI1. That's what we're doing. That's the point of changing all this. We're also changing the initial conditions to change it from a wall to a cyclic AMI. If this AMI was no slip, as it is right now, the thing would crash. It needs to be of type cyclic AMI and have a value of its internal field. We're not applying any sort of special condition. So we just say, hey, this is all what it's calculating at those positions. They just need to talk to each other. And since it's all the same, we can just copy paste this exact same boundary conditions on pretty much whatever kind of variable you're using, whether it's pressure or nu or K epsilon, K omega, K whatever. It's always going to be, unless you want to enforce some sort of difference, like a pressure difference over the AMI. But for our purposes, it's always going to be internal field. Now when we run it, it should be able to talk to each other, and it'll be just a single block in crossflow, a much smaller block. This now, when we open this up, you'll be able to see that there's continuity over the entire section, even across this gap right here. That's because the cyclic AMI allows these faces to talk to one another. The AMI is, the patch weights are calculated once at the beginning of the program, and then this face is talking to that face, this face is talking to these three faces, this face is talking to these two faces. It's recalculated each time. That's what's important about the cyclic AMI. It allows different faces to talk to one another even as they move. This gap right here doesn't matter. It can talk across it. We're going to close that gap later on in the video just because it's ugly and it doesn't really add anything to the computation. It's used there purely so it's easier to visualize what the AMI is. Two different patches connected in the blockmesh dict file so that they can talk to one another. Everything else about this simulation is completely ordinary. This is still a static mesh because nothing's moving. Next thing I'm going to do is we're going to clean the case just to make things easier to visualize. Then we're going to go here and into the dynamic mesh dictionary and just, well, confirm, I guess, that the cell zone is rotor, that we're changing, which is what's going to be rotating, and that the rotational velocity is omega and is a non-zero value, and that it is in fact going to be a rotating motion. We're using solid body so that the points don't deform relative to one another. It's just the cell zone itself that's rotating. We'll try and run this now. It won't work because we didn't define our cell zone yet. Oh, well, we didn't create the mesh met. But now when you try it, we are unable to find cell zone rotor. We have to define that in blockmesh. This is one of the two things we have to do. We'll do that now. In blockmesh, we define it right after the hex 2D, or the hex, I guess. I'll show you what that looks like in a regular blockmesh file. after we make the mesh, just so you can do it without the macros. This M4 file is not necessary at all. It just makes things a lot easier to program and use. Now when we make the mesh and check this block mesh dict file, we'll see this rotor after the hex, right? This means that this block 4, which is inside the boundary ring, is of the cell zone rotor. And when we run pimple dym foam now, instead of crashing because we didn't define the cell zone, we'll check the results now to confirm that it does what we expect it to. See how this inside moves right here? And that the rest of it doesn't, and there's still continuity in between these edges, this boundary here. These faces are talking to these faces, and it's at the correct faces because we know it recalculates it at every time step. See this AMI creating and addressing weights between 80 source faces and 160 target faces? It does that each time. It recalculates this interface at each time step, which is necessary because it moves at every time step. This is the simplest explanation for the cyclic AMI, for the dynamic mesh. I think this is the simplest thing you can do while still hitting all the elements. There are more complicated things, but that isn't covered in the scope of this video. The next thing we'll learn how to do is how to do all this not in block mesh, but in SnappyHexMesh. It's a little bit more complicated. This case file is the tutorial 17, and we're using it to show you how to make the cyclic AMI and cell zones in SnappyHexMesh. Right now, we haven't done that. And it's gonna look pretty much like the block mesh we had before, but because of how Snappy works, this initial mesh won't have anything in the center. It'll just be completely empty like this. We still have STL files in the center here, but because they're outside the outer boundary for the rotating region, we don't see them yet because we haven't implemented the face zone type, and we aren't actually looking inside here yet. We're going to run this case. We can still see that the mesh works pretty much exactly. Mesh looks pretty much exactly the way it did before in terms of static and sort of the static mesh. This is because it's really the same thing. It's just that the mesh is a tiny bit better because it's more regular on the outsides, and it's more defined close to the boundary. We're going to clean the case, take a look at SnappyHexMesh, and prepare it for the cyclic AMI. The first step is type this right here, face zone, inner cylinder. Now we're going to make the mesh and see what that does. See right now how we mesh the inside? This AMI1, that's changed. That was changed in the create patch dictionary, but that was the inner cylinder patch. That's just right here. That is just the boundary. Where we had a gap before, we now have two patches that are pretty much exactly on top of each other. That's important because we're going to have to use this inner cylinder slave in order to make the second part, to make AMI2, the second part of the cyclic AMI. We're going to do that in the create patch dictionary. We're going to change this AMI1, which was the wall, into the cyclic AMI, which we want it to be. We're going to have to do the same thing. This looks like the same thing in the block mesh. You're defining it pretty much the same way, just in a different place, which makes sense, I think. And since we have both the AMI1 and AMI2, you can just copy that. It'll all be the same except for here, here, and this AMI2 is created from the slave patch. That's important. Yeah, there has to be two different patches to be created from, which is what we did with the face zone, and this is how you put that in. These have to be different. That's what I'm trying to say. We also changed the 0-second file. This is changed the same way as in the block mesh video. That shouldn't come as a surprise because how the mesh is made shouldn't really affect the initial conditions. Again, this is just the cyclic AMI internal field. We're not changing any, we're not pushing any kind of pressure on the boundary. We're not going to change the boundary in any way. We just want it to talk to each other clearly. So, cyclic AMI internal field. Now that we got that out of the way, we can test it. We're going to make the mesh again. And then try running it from OpenFoam. We can visualize this in Parafoam. And there you have it. This is the inlet, this is the outlet. It's not moving yet, but these two different boundaries do talk to one another. And the cyclic AMI works at least. Next up, we're going to add the cell zone to SnappyHexMesh dict. This is done in the same way, in a similar way to the boundary. In this refinement surfaces right here, we declare the cell zone to be rotor, and then we say that the cell zone is inside the STL, the inner cylinder STL file. Simple as that. And now we just need to ensure that the dynamic mesh dictionary is all done. This is the exact same dynamic mesh dictionary that was in the block mesh. That's no surprise. So is the 0.original 0 file. Okay, we'll make the mesh, and then we'll make sure this works with Pimple DYM foam. Now we'll check this in Parafoam. It's moving, and there is a conversation happening between the edge of the two patches. This is exactly what we were looking for. SnappyHexMesh did pretty much the exact same thing as block mesh, just with a more regular mesh on the outside and better defined boundary on the inside. We're now going to use SnappyHexMesh for something that really couldn't be used with block mesh. You know what? That's the last part of the video. We'll be demonstrating a baffle valve done using the exact same techniques as the much simpler case. This is the tutorial 18. We're going to make the mesh. I'm now going to use parafoam. This is the valve. This will rotate counterclockwise in order to close off this section here and force the fluid through a much tighter boundary, so it'll speed up there. This SnappyHexMesh file is everything's already set up for the dynamic mesh. We don't have to change anything. It's done the exact same way as it was the previous time. Feel free to inspect whatever you want inside the SnappyHexMesh or the create patch or the topo set. It's all there. And since it's all there, we can run it with Pimple DYM foam. We elected not to do this in parallel because we didn't think that would be covered by the scope of this video, but it can be. It's not that much harder. The inlet is up here. There are two outlets, one with a much smaller width than the other one. You can see now that this is indeed moving. There is continuity between the border. Everything looks like it should. This barrier here is really just an absence of cells. We're going to go ahead and view this a bit differently with the slice, and then applying the glyphs so we can see what direction the flow is in. See how there's that vortex right here that made it through the boundary? Same here. Everything communicates. The next step in dynamic meshing, which is not at all covered by this video, is how if you had two interlocking dynamic meshes and you couldn't have a solid body rotation, it was necessarily deforming the points. That's much more complicated and will usually require remeshes at every time step. Luckily, we don't cover that. I don't feel that's absolutely necessary, but it is quite difficult. And once you've mastered this, that is the next step.